Hey everybody, welcome back. I hope you had a good weekend. We're going to continue today talking about work and energy. Specifically, I want to just focus on that work equation that we looked at last week with a few more examples, um, and get you guys more comfortable with that equation. So in the first, before we start the examples, I'm just gonna rewrite that equation that we talked about on Friday. That work is equal to the force times the distance or displacement vector cosine of theta, where theta is the angle between force and distance. And we were able to get an energy in joules, which we abbreviate as J. And so now we're going to look at a couple more examples. What I want you guys to try today, if you'd like, is try working through the examples first. See if you can do them. Maybe pause the video for a minute, before each part. I'm going to go through the parts in order. So maybe like pause the video, try part A, and then, resume the video, see if you were correct. And that might make it a little bit more fun than just, just watching the video. Might actually get you guys thinking a little bit. So feel free to try that out. All right. So I'm just going to go through example 3. And again, if you want to work ahead with me, then that would be good. And then you can kind of check your work. So in example 3, it says a 25 kilogram box is on the ground and pulled to the right at a constant speed with a horizontal rope. Assume friction exists between the box and the crate. So we've got a couple things going on here. We have this friction, that's acting between here and the ground. And so there's going to be a leftward force of friction. We have that the person is pulling it to the right at a constant speed with a rope. So, we've got some rope attached to the box, and we are exerting a force on that, and we, called that force tension. We have, as always, gravity pulling this thing downward, which we recall Fg equals mg. And then we also have, finally, our normal force, Fn, acting straight upward on the box. Right. So if you were able to label all 4 of those forces, nice work. And then let's continue onward. So now let's find the work done by friction on the box if the coefficient of kinetic friction between the box and the floor is 0.42. So we're looking at this force here. So you might need to look back at your notes in order to solve this one, in order to come up with the equation for friction. If you do remember it, friction is mu times the normal force. And, well, I don't know what the normal force was. It didn't give that to me. All it told me was that the mass was 25 kilograms. Didn't tell me anything else. Well, remember that this thing is moving at a constant speed. So this means that my acceleration in the x is 0. This also means that my acceleration in the y is 0. It's not being lifted up off the ground, which means that my force normal and Fg are equal to each other. So I can say that Fn equals Fg, which equals 25 times 9.8. And so I can write that the normal force is about 250 whatever that is, 250 newtons, a little bit less, but rounding to sig figs. And then we can plug that normal force back in to our friction equation. And so we can solve for the force of friction and this will give us a value for the force of friction of approximately 103 newtons, give or take. Now, why did I have to go through all that work of finding the force when it's actually asking for the work done by friction? Well, our equation, right, is work equals force times distance cosine of theta. And so, we need this force value in order to actually calculate this. Now, in the problem, I actually left out a critical piece of information, and we're going to actually add that in now. The it says pulled to the right at a constant speed. It's pulled to the right at distance of, we're going to say 11 meters. So I forgot to correct that, but we're going to just assume that that's the distance. Okay, so sorry if you try to solve that and could not figure out what the distance was. My apologies. Let's solve for the work now. So the work done by friction will equal the force of friction times the distance times the cosine of the angle between the distance and friction, which in this case is 180. Because friction's acting to the left, the distance that this object is moving is to the right. So we have 180 degrees between those. All right, so I can solve that, plug that into my calculator, and I'll get about a negative 1130 joules, rounding to 3 sig figs. All right. So that's it. So work's doing that much negative or taking away that much energy from this thing. Now we can find the tension done by the work in the rope. Now the tension is going to the right, and we don't know its value, and it's not given to us. So we have to use our knowledge of forces to figure this part out. If tension is acting to the right and friction is acting to the left, and those are my only two forces in the x direction, and my acceleration in the x is 0, this means that my tension force is going to also be equal to my friction force. And if this thing's moving at a constant speed, then if my forces are equal, then my work values are going to be equal. The only thing that's different here is going to be the sign. And we can show this through our math here. I'm going to use the same work force value. I'm going to use the same as the work of tension, as opposed to up here, it was the work of friction. So work of tension is 103 times 11, but the tension is moving to the right. So this time my angle is 0, which this goes to 1. And so I'm going to get a positive value of 1130 joules. It's actually the complete opposite of this. So this work is canceling with the work of friction. And that's why it's not accelerating. So, or rather, because it's not accelerating, we know these works are canceling because AX is 0. All right, and then the last parts D and E should be pretty straightforward, actually. If you remember what we talked about yesterday, it says find the work done by the gravity and by the normal force. Now, all you have to actually look at here is these angles. Normal force's angle with distance is a 90-degree angle. It's perpendicular. Gravity's is -90 or 270. And anytime you plug those angles into cosine, you're going to get 0. So for gravity, the work done by gravity, I mean, we could plug in m and g for the force and get that, and we could plug in 11, but we know that the cosine is going to be, -90 or 270. Either way, this is going to give us a result of 0. And we multiply that 0 through, which just means that this work is going to be 0. And so when you have a force that's perpendicular to the way the object is moving, so in this case, gravity is downward, the distance it's moving is to the right. Because these are perpendicular, so perpendicular forces to the displacement vector is always 0 work. And so we can actually answer the next question very simply then, find the work done by the normal force. And again, this idea that the normal force up and my displacement vector is to the right, there's again a perpendicular angle, which means the work done by my normal force is going to be 0. All right, and so now we can find the net work done by all the done to the box from all the forces acting on it. We want to be careful here about adding just all the numbers together. Obviously, these are 0, so they're not going to affect it. But you want to make sure that you're only adding. You want to make sure that you're just adding the values that are like moving relative to the distance. So if this thing was moving at an angle, we would actually be accounting for that in the fact that we would have some work done in the y and some work done in the x. And so this is because these are all scalar values. You can just add them all up, even if the work is being done in separate directions, because the equation is gonna kind of correct for that. So this is actually a little bit easier than like adding forces that were at angles with each other. Here we're always finding it relative to the distance vector, so they're already normalized for that or corrected for that. All right, so obviously these two numbers are going to cancel out. These two numbers add nothing to it, and so the net work done here is just going to be 1130 minus 1130 plus 0, which equals 0 joules. So no work is done. And the network being 0, we could have assumed that from the beginning because it's a constant speed. And constant speed means no acceleration. And no acceleration means that the kinetic energy isn't changing. The velocity is not changing. The kinetic energy is not changing. And if the kinetic energy is not changing, then we're not going to have any work done on this thing. All right, so that's this example, and hopefully you were able to work through some of that on your own and maybe answer some of the questions. And good job if you were able to do that. All right, and finally for today, let's go through this page here. Example 4. So here, I don't know, we have some grocery cart. It's a beautiful grocery cart. And it's being pushed at a constant speed along an aisle by a force of 12 newtons. It's probably, filled with like toilet paper because, apparently that's all the craze right now. And we're locked inside our houses, so better have toilet paper. Maybe there's even like, some bigger rolls here. It's like overflowing with toilet paper. But, the person that's pushing this thing, they are psyched because they're ready to go. They're like, COVID-19, I got this. They're ready to just crash in their house for a couple weeks. Play that new Call of Duty game. Good stuff. All right. So there are 4 forces acting on the cart. We're going to go ahead and draw and label those. And these are going to be very similar to what we had in the last example, right? So if you want to go ahead and give that a try, and I'll label them here. So it does say to assume friction exists between the cart and the floor. So there's some friction in the wheels here. It's not perfect. We're going to lose some energy there. So there is some frictional force acting to the left. We have a same force of gravity going downward, pulling this cart to the ground. We have some normal force pulling it up, and then we have our push. Now, oops, I drew this a little bit incorrectly. It says the force is acting at an angle of 20 degrees below the horizontal. So if I drew my horizontal here, the force of the push is actually going to have a slight angle, 20 degrees here. All right, so there's our four forces. It says the aisle is 15 meters long, and so, our distance here is going to be 15 meters. Each of these forces moving at constant speed. So the force on the cart is 12 newtons at an angle of 20 degrees. And then there's friction. It's moving 15 meters. So that's all of our pertinent information to solve the rest of this question here. So it says, what's the work done by the 12 Newton pushing force? And so again, you can kind of think of this in two ways. You can think about it like in terms of just the push force relative to the distance and use that 20-degree angle, or you can get the x component of it like we did before and then use the x component. Either way the math works out, I think it's easier probably just to think about it with the whole force. So the work done by the push force is equal to 12 newtons of the push force, distance of 15 meters, and then cosine of 20 degrees. And we can plug all that in, and we're going to get 169.1 joules for our answer for part B. And then it says find the work done by friction on the cart. And so hopefully you're able to answer this question almost immediately. You read that it's moving at a constant speed. This is really, really important here. And so if it's moving at a constant speed, that means that so constant speed means that force of friction equals the force of push. These are equal and opposite forces. So this means that the work done by friction is just going to be the opposite amount, or negative 169.1 joules. All right, find the work done by the normal force on the cart and the work done by gravity. Like we talked about in the last one, these are both perpendicular forces, 90 degrees here, 90 degrees here. And so we can simply write 0 for this. The work done by the normal force is 0 joules, and this is because theta equals 90 degrees. All right, and then the work done by gravity is going to be the exact same thing. It's going to be 0 joules as well. And this is because theta equals 90 degrees, or sorry, negative 90 degrees or 270 degrees. All right, and that means my total net work net, is also going to be 0. If we plug in, 169.1 plus 169.1 minus 169.1 plus 0, we get 0. All right, and so that's it for this lesson. Hopefully you guys feel more comfortable with this equation, FD cosine theta. That's really what I wanted you to get out of this. So this equation is in joules. If it's a positive amount, it speeds the object up. If it's a negative amount, it slows the object down. And we're going to be, again, using our force diagrams that we've been using in order to help solve these problems. All right. And so I'm going to give you guys a problem set tomorrow, and you'll be able to work through some of these examples. So please go back to these 2 pages in order to help you solve those problems, and email me if you have any questions, or drop into my office hours, which are going to be, I think, 1:30 for you guys every day. So I'll be online. You come into Teams and you can chat and ask me any questions you might have. All right. Thanks, everyone. I will talk to you in a few more days.